lecture for Chapter 5, Chapter 12, Physics 1101, Chapter 12 on sound. All right, so we'll talk about sound. This will also be related to Lab 12, which is on sound, standing waves of sound. So we'll be talking more characteristics of sound, sound waves, resonance, speed of sound in this chapter. So, go through this today. All right. So we talk about characteristics of sounds. We talk speed of sound, which is approximately 300. Well, the expression is 331 plus 0.6 times the temperature, which is in degrees Celsius, is the speed of sound. If T is 20 degrees, so about room temperature, then V is about 344 meters per second. And that's what we'll be using for many of the problems here. So this is the speed of sound in air, right? Now if you look at the speed of sound in other materials, we'll bring this up here. You look at other ones, speed of sound in air is 344 or so. Helium is about 1,000. Water, 1440. And iron's about 5,000 meters per second. So actually about 3 miles per second. So when this is in air, so it's air, then liquids, then gases, then solids. Now part of it is the fact that for helium, it's about 1,000 meters per second, which is about 3 times faster. It's because helium is so light, the molecule vibrates so much faster as a very light molecule, so it has very speed. Now if we go back to our Russians, is velocity is frequency times wavelength. So if we have a much higher speed for a given wavelength, then the frequency is going to be much higher. And this is where we get the characteristics, have you ever heard, and I've got one of the videos posted of if you have breathe in helium and talk, you sound like Donald Duck, you know, really high pitched. On the other hand, if you have a very high gas, very heavy gas, such as sodium hexafluoride, then that gas is very heavy and it makes you sound very deep. So I've got a, what is that? Oh, short little video clip showing how that is on the chapter 12 link, showing the characteristics of that. Okay, so that's the parts of chapter 12 as far as speed of sound. All right. Now again, sound in air is a compression wave. Because in gases, the air can only go back and forth. It can only vibrate back and forth as the wave travels this way. So it's like a slinky that vibrates back and forth. Wave travels that way, the molecules vibrate back and forth in the same direction, as opposed to a shear wave or transverse wave where they vibrate perpendicular to the pointed direction. All right, so that's what we'll be looking at here as far as that's concerned. So, all right. Now moving on, and again, this chapter is the first chapter for the final exam, for the exam 5, which will be on chapters 12, 13, and 14. All right, so now we're going to get into intensity of sound. And this is the decibels. I'm going to spell decibel. Okay. Intensity of sound, and that is, we look at the threshold of hearing, all right? Now intensity, if we have sound is power, intensity is power over area. Now power is given in watts, area is in meters squared, so these are units of sound intensity, and it spreads out, right? So it spreads out, and since the area of a sphere is 4 pi r squared, the intensity drops off as 1 over r squared. Meaning if you double the distance, if you go from say 1 meter to 2 meters, the intensity here will be, at this point, will be 1/4 of what it is at this point. So this is what we call I naught. This will be I naught over 4, some intensity. So it spreads out as the square of the distance, much like light does. We'll see later on. Anything that spreads out, what we call isotropically, goes off as 1 over r squared. So we look at power, or sound intensity. We're going to talk about power, watts. Remember we had watts from before, joules per second. All right, the range can be what we call the threshold of hearing. This is approximately 10 to the minus 12 watts per meter squared. All right? The minimum a person can hear. Our hearing intensity is, sensitivity is very good. If we talking, it's about 10 to the minus 6th. And if we have a jet plane, this can be on the order of 100 watts per meter squared. And then if we want to go really extreme, up to, say, right near the space shuttle launch, it could be as high as 170 watts, or 100 watts. It can be as high as 10,000 watts per meter squared. So a shuttle launch, a rocket launch, all right, so these are a huge range of many orders of magnitude. So to avoid these scientific experiment, we do what we call the decibel scale. And the decibel scale is given as, we call beta in units of dB is 10 times the intensity over what we call I naught. I naught is the threshold of hearing, and that's 10 to the minus 12. So it's this intensity, so 10. So threshold of hearing, so this is the decimal scale. It's a logarithmic scale, much like if you're in chemistry, you have the pH scale, which is logarithmic in concentration of powers of 10 of hydrogen ions or OH ions, depending on what you're trying to do. And so this is the expression. And so we have threshold of hearing is then defined as 0 because, log 10 times the log of I over I naught. Sorry, it's 10 times the log of that. So threshold of hearing is 0. This would be 60. You can calculate yourself. A jet plane. This is 10 to the 14th. This is 10 to the 14th greater. So this would be 140 dB. And this would be 10 to the 4th. This would be 160 dB. All right, so this is what we call this. You can calculate this. Let's do this as an example. So for talking, this would be 10 times the log of 10 to the minus 6th over 10 to the minus 12th, which is 10 times that, which is 10 times 6. Log of 10 to the 6th would be 6, so it would be 60 dB. So that's our expression for intensity. And so we have this compare. So for talking then, it's 60 dB. So let me go with some other examples comparing this, which is really what we're going to do. So again, our expression, dB is 10 times the log of I over I naught, or I over I naught, or I naught is 10 to the minus 12th. So again, we have one person talking, is 60 dB about. If we have, this is a factor of 10, logarithmic scale. If we have two people talking, it actually increases, when you double this, it only increases it by 3 dB, 63 dB. This is what we call 3 dB. It's either an increase, a doubling means we increase by 3. If we have 10 people talking, it's going to be 10 times, right? This will be 70 dB. Every factor of 10 is an increase of 10 dB. So if you have 100 people, that'd be 80. If you have 1,000 people somehow in a room, that would be 90 dB, right? And then if you get 10,000, then you can get very loud, like in a stadium. You can get extremely loud intensities. So it's an increase. So increasing by a factor of 10 is 10 dB. Increase by 100 is 20. And increase by 1,000 is 30 dB. So this is the decibel scale as we'll be using in that case. Right? All right, now we're going to go on to next part, our vibrating columns of air. All right, and again, this is related to Lab 12 on sound intensity and resonance. So we'll get into that a little bit. But we have a vibrating, we'll go into this of resonance. All right, we began a standing wave like that. This is L, the fundamental, the frequency, the length L is 1/2 lambda, 1. So this is what we call the fundamental. The next one does this, where L is lambda 2. And the third one does this for L is lambda 3/2 lambda 3. All right. And if this is 100, so if F is 100 here, then this would be 200 hertz, and this would be 300 hertz. So each harmonic, 1, 2, and 3, are multiples frequency of that. So this is what we call staying away. This is actually what we would have on a vibrating wire. If it's vibrating for like a string instrument and such. Okay. So we're gonna go, while we're on this, I'll go on a little bit of harmonics and stuff. And if we have a simple tuning fork, okay. This produces a single frequency. In this case, a simple tuning fork has frequency of 480 hertz, which musically is the B, but it has a very simple sound to it. If we have something more complicated, say as a violin or a piano or a clarinet, right, they have distinct sounds to them. But if we play a B, which again, 480, a B on a violin does not sound like a B on a tuning fork. It has much more rich sound to it. And in this case, what it has are overtones. Right? And the way we can do this is by, we graph amplitude versus frequency, right? Then for a simple tuning fork, it has one note at 480, and that's it. So a tuning fork has that. A violin, on the other hand, as if we play B, as first harmonic, a second harmonic, third, fourth, and fifth, and so on. So this would be 480, 960. So it has different harmonics that all add together in just the right way to give the unique sound of a violin. And it sounds different if you just pluck it, and it sounds different if you bow it. So this is the sound of violin. So it's all these harmonics that add together that give that characteristic to it. I got a picture from the book here that shows a violin, as we see there, is for a piano, and this would be for clarinet. Notice how they're all, the harmonics, they all play the same. If they play B, it's the same note, but the other harmonics that add to it give it that unique characteristic. It's also why if you can synthesize the same kind of sound on an electronic synthesizer by reproducing this exact characteristics, will sound like violin. So like a digital piano. It sounds like a piano, a violin, a trumpet, whatever, based on doing that. So these overtones, again, tuning forks is just one. The other instruments have other overtones or harmonics adding to it. All right. So while we're on that, so a clarinet is a woodwind instrument. It vibrates inside. And if we look at lab 12 is based characteristics of if we have what we call an open tube, meaning it's open at both ends, and the closed tube, if you look at lab 12, so this is lab 12 basically, right, which I show for you. It's closed at one end and open at the other. And I can't draw these very well, but if you actually look at the intensity, so for an open tube, all right, we have harmonics. Open tube, the harmonics are, there's the top one is the fundamental, the next one is the second harmonic, and the bottom is the third harmonic. So for an open tube, we end up with just harmonics and multiples. For a closed tube, meaning it's closed at one end, the pressure waves, which produces loudness, are, instead of just 1, 2, 3, are just the odd harmonics, the only ones that came through. So it'd be 1, 3, and 5 for those characteristics. And that's part of lab 12. So if we look at that for an open tube, F1, F2, F3, this would be 100 hertz. If that was the fundamental, this would be 200, 300. These would be, and so on. For a closed tube, F1 was 100 hertz. Then F2 would be 300 hertz. F3, there is no F2. The next one would be the odd. So only the odd harmonics in a closed tube will resonate or produce a resonant sound. So 100, so odd. The even ones do not exist. All right, the even harmonics. Now again, if it was like 200, doesn't mean you can't have even number. Then it would be 600, 3 times that, 600, and then 5 times 1,000. Okay, so if this is the fundamental, it would be 3 times that. Okay, and then 5 times that. All right, so that's what we have for, this is how lab 12 is, and that's the section on 12.4. So this is section 12.4. I mean, lab 12 turns out to be the same coincidence as part of that. All right. Last couple things here. We'll get into beats and the Doppler effect. And that'll be the end of this section. All right. The beats are if I have 2 sounds, and I'm not sure I could do this right. All right. If I have 2 sounds that are slightly different, so beats. All right, so if any of you ever played an orchestra or trying to tune a string instrument, you'll hear a beat sound. And what this beat sound is if you are close, so if somebody's playing A440, hertz. And if you are exactly on the same, it will sound there. You'll hear a very smooth pattern between the two, right? They're both 440. So if this is A, somebody's playing that, and you're playing 440, you'll hear the same constant sound. However, if you're playing say 442, you will hear a beat pattern based on interference, because as you see in this figure here, all right, they're slightly off. All right, you'll get a beat pattern that gets louder and softer. Here's whoa, 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 whoa. And the beats are given by, so this is F1 and this is F2. The beat frequency is F2 minus F1, or just the difference in the two cases, and that'd be about 2 hertz. So you would hear a beat pattern of that. Now the limit that we can actually hear is about the difference, maximum delta F, or frequency. It's probably on the order of 10 hertz. Beyond that, it's hard to tell this beat. So let's see, once every 10 hertz. So if we had 440 and 460, the difference here is 20. You would not be able to hear that. You would just hear, again, a constant sound, but you wouldn't be able to tell which is what. You have to be relatively close to that. So the maximum is less than about 10 hertz is the difference. So they have to be relatively close to each other in the first place. So if they're way far apart, you're not going to hear that. So this is beat pattern, and it's given by this expression here. So 2 sounds of relatively close frequency will give us this beat pattern. Okay. And the final section we do for this is so-called Doppler effect. And this is named after Christian Doppler, who in around 1853 or so, in Salzburg, Austria, which, if any of you know about music, is the birthplace of Mozart. We got 2 museums there. They don't have much on Christian Doppler. And what the Doppler effect is if I have, say, a tuning fork, what I have here, as it moves towards you, this sound vibrates, sound sending out. If it's moving towards you, you hear, if this is 480 hertz, if it's moving towards you, you're going to hear a frequency greater than 480 hertz. And if it's moving away from you, you'll hear a sound with a frequency less than 480 hertz. And this is the so-called Doppler effect, right? You hear it like when a car passes by, train passes by, as it's coming towards you, you hear one sound, higher pitch, and just as it passes by, as it leaves, you hear this change in pitch as it passes by. So this is the Doppler effect, and it allows us to determine what the frequency would be for a sound coming towards you or leaving away. It's also used in light, astronomy. We call redshift or blue shift. If we see a blue shift, it's coming towards you at a certain speed. If it's a red shift, it's moving away. So we'll get into that later as far as that is concerned. So if it's coming towards you, the waves beat, and it's going to be slightly higher. If it's moving away, it's going to be slightly lower. For this example of 480 hertz. So let me go through the, give you the actual problems here. So we're going to look at two different cases. Either you are standing and the source is moving towards you, or the source is stopped and it's moving towards, you're moving towards it. So here's what we're going to have. Okay. So for the Doppler effect, all right. So observer moving, so that's you. Okay, we have the frequency we detect is given by 1 plus the speed of the observer over the speed of sound, which in this case, the speed of sound is 344 meters per second times F. So that's towards source, away. Okay. And in the case, if it's moving away, then F prime will be 1 minus V observe over V sound times the frequency. Notice here, if we're moving towards it, we're adding it to it. Here, we're subtracting it, where this is the speed of the observer. And if it's moving away, source moving, or again, we got speed of sound, source moving, and this is all in the text book on page 346. In that case, toward observer, then the expression is F prime is F over 1 minus V observer over speed of sound. And if it's away, then F prime is F over 1 plus. And so again, if it's moving towards you, it's going to be higher because this will be a number less than 1. And if it's away, this will be lower because this denominator is a number greater than 1. So these are examples for observer moving based on the speed of the observer. Oh, speed of source. It should be source, not observer, because you're stationary. In the second case, you're stationary and the thing is moving towards. So if you're standing and a train is coming by you, this would be the case here. In this case, when it's first coming towards you, and the bottom is when it's moving away. So that is the characteristics of speed of sound. There's a little bit on a Doppler effect, based on the fact that, again, the speed of sound is about 344 meters per second, or approximately 750 miles per hour. All right, so that's the sound. And that's how we call the sound barrier, meaning beyond that you produce a sonic boom if you go faster than that. Okay, that is chapter 12 on sound. That ends our parts on sound. The next 2 chapters will be on temperature and on heat. Right? Again, that's chapter 12. Have a good day, and I would suggest